Cool. Okay, so today we're going to discuss coding patterns, a couple of very important coding patterns and their variations, which is DFS and BFS, depth first search and breadth first search. They're very important patterns, like probably the most important patterns, because they help us solve so many questions. All right, yeah. So before we start, if anyone has any comment, question from the previous session, otherwise we can move ahead. All right. So this is grokking the coding interview. You can actually come here to see these patterns that we discuss. So let's start with the BFS. Okay. Yeah. So as I said, these two patterns, they're probably the most important patterns because they're applied to so many data structures, especially trees and graphs. But as we will see, also they're applied to matrix, because matrix traversal can also be seen as a graph traversal. So in short, at a high level, these two strategies, the BFS and DFS, they help us iterate or traverse a graph. And then tree is a graph, matrix could be a graph, and we'll see there are a couple of other patterns. The set subset pattern, which is also a traversal, a graph like traversal. And so the same strategy applies over there. I've seen so many questions in interviews, and people have actually experienced that these two patterns, they end up solving so many questions and coming up in interviews again and again. If I'm not exaggerating, I think it's 30-40% questions will be solved some variation of these two patterns. So they're very famous. You guys might have the idea about it, but we will first see the how they work, and then solve a few problems of each pattern, and then eventually we'll also see the matrix, which is a little variation of the graph traversal. But that will help us understand how different data structures can be actually traversed using these two patterns. So in a BFS, how do we do it? In a breadth first search, we traverse in a breadth first manner. For example, in this tree, first we traverse one, and then these two nodes, and then these four nodes. That is the breadth first level, you can say. Level by level traversal, or we actually traverse all the nodes of a level, or you can say all nodes that are same distance from the root. For example, this node 2 and 3, they are distance 1 from the root, which is 1. Similarly, 4, 5, 6 are distance 2 from the root, so we traverse them together. As compared to DFS, you can say, so in DFS, we go all the way, and we actually go deep all the way in a path. For example, in this case, we first go 1, then we go 2, and then we go 4, then we come back, kind of thing, and traverse 5. Then we go all the way back and start doing 3, and then 6, go back at 3, and come back at 7. So it's a recursive way, kind of, but you can use it. You can traverse it using stack too. At a high level, you should keep this thing in mind, that you'll use a queue to traverse in the breadth first manner, and a stack or recursion, which is actually using the the system stack to traverse in the depth first session, the depth first manner. Let's see, how do we do it? Let me share the screen. Let's see. Okay, so let's go back and come here and see how we do it quickly. Let's see, I'm gonna try to draw this tree, which is 1, 2, 3, 4, 5, 6, and 7. So we will actually use a queue to traverse this tree in a breadth first manner. So we are doing BFS, and we use a queue. It always starts with pushing the root node to the queue. So let's say this is our queue, and we push the root node at the queue. So now we'll take one node from the queue and traverse all of its children. And by traversing means we're going to push them in the queue, traverse this current node and traverse all of its children. So for example, one is here. We'll push the one in the queue and start traversing, start iterating through the queue. We'll take one out in the next iteration and push, like you can say this is 1, and we push 2 and 3. We take 1 out and push 2 and 3, which are the children of node 1. In the next iteration, we'll take, you can say 2 out, put 3 here, and push the children of 2 into the queue, which is 4 and 5. Okay, so in the next iteration, we'll take 3 out, and 4 and 5 are already there. And what are the children of 3? 6 and 7. Like similarly, you understand, in the next iteration, we take 4 out, and there are no children. So if you see, we did 1, 2, 1, 2, 3, 4, and then 5, 6, 7. 1, 2, 3, 4, 5, 6. This is the breadth first search. So we use a queue to keep track of the nodes of the next level. And this way, we always do this zigzag traversal, this one, and always actually this one, from the left to right. So let's actually see this problem to quickly see the BFS in action. BFS is kind of a level order traversal, and this problem is right. You can say the BFS kind of problem, binary tree level order traversal, we call it. So we are given a binary tree, populate an array to represent its level by level traversal. So we need to do level by level traversal and then populate an array, which so for example, this tree has 3 levels. Level 1 has just 1 node. That's why we put it in the first node, first list, then 2, 3, and 4, 5, 6. So the only difference this problem has with the generic BFS approach is that we need to understand, where is the level breaking. So we need to know, okay, this level has these many nodes, so that we can actually start creating a new array. So we need to do the BFS, but we need to find out a mechanism which can tell us that how to find out if the new level is starting and the previous level has ended. So let's quickly see the code to understand this approach. Okay, let me increase the size. Okay. Okay. So how do we do this thing? So this is the, you can say, let me change the font. This is the, so yeah. So this is the BFS approach. So this is the result array, which will actually contain all that list. So this list, the 1 and 2, 3 and 5, 6, 7, 8, 4, 5, 6, 7, all this result will contain that. This is just a basic check. If root is null, we can leave right away. That's where we create a queue and push the root to the queue. So that is how breadth-first always starts. Take your first node and push it to the queue, and then have a while loop which keeps iterating until the queue is empty. So this particular line is the only difference from the BFS. This is how it is figuring out the number of nodes on that particular level. So whenever we are starting starting iterating the queue, we actually take the size of the queue, and that size determines that, oh, how many nodes are there in that particular level. Then we create a current level list in which we'll push actually all the elements of this level, and eventually push this current level list into the result array that we have created in the beginning. So this current level will contain all the nodes of our current level. So over here we have actually started a for loop for these many nodes, level size nodes. So in the beginning we have just one node, so which means this level has only one node. So this for loop will run only for one node, and this will always be true for trees because trees always have one root. So what we do, we pop left, like we take out one element from the queue and we append it to the current level array list. And then we do this thing, which is if we have a left or right child of the node that we have traversed, we push that into the queue. So after, for example, first iteration of this complete for loop, or when we finish iterating this for loop, we'll have two more nodes, because, for example, one was here and this was in the beginning, and we take out one, and now we push 2 and 3 to the queue. So we'll go up, and this level size will give us now 2, and then we'll iterate this for loop 2 times to take 2 nodes from the queue, and that would be our current level. And we will push all the nodes of all the children to the queue. At the end of the for loop, we push it to the result, and finally we return the result. So this is pretty straightforward, but I guess the important thing is just remember this thing, how to take an element from the queue and take the children of that node and push those children to the queue too. That's the only. So overall, you can say so this part is this part, and generally the while part, the queue and the queue. So this is the generic part in every BFS code you will end up writing. If this for loop is only here because we wanted to do it level by level. Otherwise, if you are just traversing all the nodes, you can actually you don't need a for loop. You can keep iterating until the queue is empty and whatever you want to do with each node. So any questions so far? Okay, so if you see, what would be the time complexity and space complexity? Time complexity, if you see, we are only iterating each node once. So this the whole while loop will not traverse any other node more than once. So which means overall the time complexity is order of n. Space complexity in this case is order of n, because we need two. One is the result array and the other is the queue. So this queue can contain at least like half of the node at worst, you can say. So if we have a complete binary tree, like then if you know that in a complete binary tree, for example, in this one, the last level will have n by 2 plus 1 nodes. Like, so we have like 7 nodes overall, and all the levels have 3 nodes, and the last level is 4 nodes. So all nodes of all levels. So overall, we can have n by 2 nodes or more than, actually, because when not more, yeah, at least n by 2 nodes. Yeah, we'll not get more than n by 2 nodes anytime in the queue. So which means overall you have a space complexity of order of n. If you consider result array, then definitely, since all the nodes will be in the result array, so that is order of n. But eventually this queue will contain all nodes, and at some point it will contain at least n. It can, in the worst case, can contain n by 2 nodes, which means the space complexity is order of n2. So yeah, so there is no other efficient way of this is the most efficient way of traversing BFS, and it needs order of n, space, and time complexity. All right. If you don't have any question, we can move on to the next question. Okay, so reverse level order. So this question is, given a binary tree, populate an array to represent its level by level traversal in reverse order. That is, the lowest level comes first. So there's not much difference. The same tree traversal, if you see, instead of like one coming in the beginning, one comes at the end. So each level is there, but we have the reverse order in the output array. So if you see the code, what's the difference? If you see that the same code, same queue initialization, same size, same current level, we take the node, we appending the node in the same way, same these two lines. So all this code is exactly the same from the previous approach, just this one line, append left. So when we are appending the current level to the result list, either we append right or append at the end or append left, which means at the beginning. If you see Java's code, so how does Java do it? Okay, result.add at 0th index. So they have this function to insert the level at the 0th index, which means, yeah, it's pushing all the elements to the right. So that's how Python does too. So there's not much difference, but I mean, overall in this course, in the pattern, if you see, so it tries to increase the complexity of the problems step by step, so that we understand properly.
Hey, Arslan.
Yeah.
Is line 33 needed for this, or am I missing something? So in this case, basically, I mean, we're just creating the list for like each of the sub lists, but like, I thought that was already being done.
Yeah, that's an interesting question. Why are we doing it? Okay. There's another difference. So this current level we are appending, append left. What is the result? Result is a DQ. Okay, so there's a difference actually. Result is a doubly linked list. It's a DQ as compared to the previous one. Let me confirm over there. It's not a DQ, is it?
It's just an array or a list.
It is just a result is just a list. Here, yeah.
Is there a reason why in this solution or this problem that it's a DQ compared to just a normal?
Yeah, it's because of this function. I think appending left, that's why it does it. We could do it with the array as well, right? We can insert. I think arrays insert function can do this thing too. I think so.
I'm pretty sure it can.
Yeah. So yeah. So since it's used a doubly linked list, you can say a DQ, and so that's why they have to, since they have to return the list. So that's why they wanted to do this thing. But you the idea overall you can understand. So when you insert insert a number at the beginning of a list, then you push everything ahead, which is like, this is an order of n operation. If there are n elements, push 0, push everything. So it's an order of n operation. It's true with all the lists, unless it is a doubly linked list, unless it is a linked list. So that is actually a good discussion over here. So
So would that turn it into like an n squared if we did a normal, like just array, because for each value we are performing that same action?
Yeah. So this operation is order of 1 operation. That's what I'm trying to say, because it's happening in a queue, which is just appending a node at the beginning of and just updating the pointers. But if you're using it as a list, then you have to push everything ahead. That's true with since the default list in Python is actually it's a dynamic array, as they call it. You can push, you can insert elements, you can delete elements, as compared to the Java where you cannot insert an element. You have to use this result has to be a list, a linked list, to efficiently do it. Otherwise, if you use a similar strategy over here, Java and C#, all these have array list. So array list and Python's list are the same. C++ vector is the same too. They are all, can I move this thing? Oh, yeah, okay. All right. So this was interesting, actually. I totally missed that. So thanks for pointing out. And this is very crucial. I actually failed an interview by not explaining this thing. That, okay, this is a list as compared to a queue, a linked list versus a dynamic array, because dynamic arrays has other problems as well, like not problems, you can say that's the nature that you have a fixed size, but as you grow, you can grow a dynamic link list. So as you grow, you have to allocate a new space, which is generally 2x or 1.5x, move all the elements to this new space, and then insert more elements to it. Similarly, you can delete an element, or if you insert, you have to push everything. So whenever you are inserting an element, always think that you should use a list, a linked list, I mean, which is DQ or Q in this case, not the simple list, because it would be an order of an operation. All right. Other is this zigzag traversal. Zigzag means that, okay, first level 1, the other is 3, 2, and then 4, 5. Like one level is from left to right, the next level is from right to left, then left to right, do the same thing. So that is, again, it's very simple. The only thing that we, I think, do differently,
use the DQ for a current level.
Yeah, the current level is DQ again because of this insertion. And we pop left, and if it's left to right, then you append, which is append right, you can say. Or if it's right to left, there's this flag, which is okay in every level. You gonna so this thing, right? If I so because of this, when you are done iterating a level, you change the flag to the true to false. And so these two condition, if else, it's telling us either I need to append at the end or at the beginning. Otherwise, the code looks same. This is that result appending, toggling the flag, and this result is, yeah, we're always appending this thing over here. So from the current level, we have to, which is a queue, we have to create a list to insert it. So overall, I guess just using a queue and then using a flag, these two are the big difference. This is your main change of code. Otherwise, it's quite similar to the first problem. Level by level. Yeah. Okay. So this was quick too. I guess you guys have an idea. These are very simple questions. What else we can do? Like, okay, this is like connect level order. Siblings. It's like it's saying we have to connect all the nodes of the same level in this way. Like 2 is connected to 3, or 4 to 5, 5 to 6. That's how. How do we do it? It's very, I guess, simple enough. The other thing is important is we have this next pointer given, which is none by default, but this will be populated to point to the next node. This is just the printing. We don't need to really think about this. Over here, what do we do? Queue, same root appending, previous node. Yeah, we need to take care of the previous node so that we can actually set the pointer of the previous node to this current node. Okay, yeah, so that is the most crucial point. Have a previous node in the while loop. Then again, we have the level size. We have to find the level size because then we have to do this for loop so that we iterate those many nodes. We take out the node, and if the previous node is not null, we set the value to this current node, and the current node becomes the previous node for the next iteration. So if you see, when we are done with this for loop, we go up and set the previous node to none again, because if you see this thing, so the last node is always pointing to none. It's not that if we don't do this thing, this previous node to none, then this 3 will start pointing to like 4. So there's just a small thing to remember. Yeah. Okay. Similar, if you see the same time complexity and same n by 2 nodes because of that, and then we have and all of them have similar space and time complexity. Any question or thoughts? Otherwise,
sorry, question. So when we do, so initially the previous node is null, right? And then we do previous node dot next is the current node. So that means null dot next is current.
Oh, if the previous node, we have if.
Oh, yeah. Sorry. I'm sorry, I missed that.
Yeah. Yeah. It's yeah, you could easily miss it in an interview if you don't put it. It's a bug. Yeah. So the first node does not have a previous node, and the last node does not have a next node. That's the, you know, boundary cases. Yeah, always have these boundary cases in when you are testing, and even it's better to, you know, write them on the board or wherever you're writing, to show the interviewer that, okay, you not only understand this, but you are also putting a focus over here, this too. So what happens, like overall in an interview, you should target you should always assume that you're gonna be asked 2 questions of generally medium complexity, or if you are going to bigger companies, they might ask you a medium and a hard question. So which means you have like 40 minutes to solve 2 questions. So 20 minutes, 1 question, that should be your target. Generally 10 to 12 minutes to devise the strategy, and then just 8 minutes to write the code and test it. This is pretty, you know, pretty complex, or like you need to be very efficient. And this can only happen, for example, if you know it's a BFS or DFS thing, then you really know what are the code lines of a BFS. So BFS and DFS are those patterns that you should remember or memorize their lines. It's like, I used to call it like, you should be able to write it with your eyes closed. It is that important, and it needs to be that efficient. Any minute you save solving the first problem will help you spend more time to the second problem. All right. Okay, so let's move on to the depth first. It's just simple. We can actually simply jump to the. So as I said, in the breadth first, we do it. We go all the way in one path. Like we do 1, then we 2, 3, then we like come back 2 and traverse the other child 5, and then we go all the way back and traverse 3 and 6, go back, and then come over here 7. So people who are very comfortable with the recursion, whenever they see you know, a problem which is being solved by DFS or BFS, a lot of problems can be solved by both the techniques actually. So they prefer actually DFS, because DFS code can be solved through recursion, and recursion, if you have a good grasp on recursion simplify your code. But it make your logic a little complex, because you have to visualize the function call. Either you can use a stack or you can use the recursion. First, let's see that, and then I'll explain a little bit on this thing. So for example, let's see this problem. Given a binary tree and a number s, find if the tree has a path from root to leaf such that the sum of all the node values of that path equals s. For example, in this tree, we are given the value s is 10. So we need to find a path from root to leaf in which the sum of all the node is that number 10. In this case, it's only this path 1, 3, 6. And we just, if we find any path, we just return true, and we can finish our search. So this problem right away, you know, telling you that you need to use a depth first mechanism, because you're trying to go all the way deep to find out if the path is fulfilling the requirement. You cannot really use depth first here, right? If you first traverse 1 and then 2 and 3, there's no way you're gonna actually, either you can, it would do it. I mean, yeah, if someone wants to really do it, they could do it. But then you have to keep storing the sum of each path separately, so that each level you take the parent's sum and go. That would be a little complex thing. But DFS is simply telling you, yeah, because we wanted to go all the way to the leaf to find, if the sum of this whole path is required sum. For example, 1, 2, and 4, would be 7, and 7 is not 10. So we go back at 2 and then traverse 5. So 2 means over here we have the sum 3, and 3 plus 5 is 8, 2, and then we come back. So we have to keep a running sum being passed to all the function calls, you can say. Let's see the solution. Yeah, that's what we have explained here. 12, we start with the root, go to 7, 12 plus 7. Like, okay, the overall sum required was 23. When you are at 7, they reduce the sum by subtracting 12 from it. So required sum is 11. When from 7, you go to the next node, so subtract 7 from your previous sum, which is 11. So now 4 is required, and go to 9, and 9 and 4 does not match. Means like 4 means we pass 4 to the next call, and we expect that the path down the hill will come up with this sum 4. If it does not, then go back and we have the sum 11 again. Let's see the code actually. So essentially, if you see there's this one line, there's this second 2 lines, then this is just a check. So the overall code is very simple, but it can become complex quite easily. So over here we are using the recursion. So this function has path. It's been called by the main function, and we will given by the root and the sum. Sum is that S number. If root is none, return false. False means there's no path. Yeah, we'll understand this thing. Let's see the recursions, and then we'll see. So in a recursion, generally you have this is the base check, you can say, where you want to break your recursion, and this is your original, this is your like the requirement check, which means, oh, we have successfully found a path. What it says that the root dot value is equal to sum, that whatever the value this root has is equal to the number which is required, and this root is a leaf. So root dot left is null and root dot right is. So if we are at the leaf and the sum which is required, and the sum that is required is equal to the current value, which means we have actually traversed the whole path. We have reached at the leaf, and that leaf has exactly the same value which is required by the number sum. So this is our termination condition. Otherwise, call the same function recursively, call it to the left child, and subtract the sum from the current value, or there's this or, and then call it to the right. So what will happen, right? So from 1 will come, and this 1 will be will fail this condition because it's not a leaf. So we go down and call the left child, which is 2, call this recursive call and pass the sum, which is sum minus the root value. If sum is 10, so 10 minus root value is 1, so 9. So this would be like call it node 2, and the sum minus 10 minus 1 is 9. So that is how we call it. So when you call this thing, so this thing is not called. So now this 2 node will come, and it has 2 children, and it will call to 4 and 5, and this will keep going this way.
Wouldn't we want to add some sort of check so that if the sum is either negative or,
yeah,
I mean, or not ever going to hit that,
yeah,
I guess, hit that path, then,
Hmm.
because I feel like we could be making like unnecessary.
Hmm. So,
Um,
so numbers can be positive or negative. Did they say positive? Yeah, they did not say anything. So if a node has a negative, you can go negative, and then the next node becomes positive, or like this sum will keep changing. The only thing you need to worry about is if you have reached a leaf, and this node has the exact value that is required, then we return true. Otherwise, let's say this is a leaf node and the sum is not equal to that. For example, in this case is 4, we are at the fourth node or 4 node, right? At that point, the sum required is 1, 2 minus 3 is 7. So 7 is not equal to 4. So what will happen? These two calls will happen, this one, and they both will return false because of this if. Because both of them are called on the null node, because the 4 has 2 children, both of them are none. So it will come and it will return. So so if you go positive, negative, we don't care. We have to go all the way to the leaf node, because the sum could vary. It can start incrementing, start decrementing based on the value of the node. But there's no other option but to exhaust our search, going all the way to the leaf and finding out if the sum of all the nodes somehow becomes whatever is required. Did I answer your question?
yeah, so I guess I just didn't read above that. I guess the nodes could be positive or negative. I just
Yeah.
assumed positive. So
Yeah. Yeah. So that's another important thing to, like, in the interview, to save time. If they're not saying anything, means you should assume. We have not actually given an example. Generally, it's a good idea as an interviewer that we should give an example with negative numbers too, so that you don't get confused. Or sometimes if you people want to make the problem statement a little vague, to let you figure out. Okay, so this was very interesting. See, if you want to use a stack, you can actually use a stack here. You can actually use like stack and push the, you need to have a loop and push, for example, 1 in the beginning, then you go in the loop and pop one element from the stack, and push 2 elements on the stack, which is, in this case, would be like 1 and 10, you can say, would be the first node, and the 10 is the sum, and second is the root dot left, which is 2 and 9, 9 is the remaining sum, and similarly 3 and 9. Okay, and then go back and actually get the element from the stack. In this case, if you see, I push 3 after the 2. So in this case, we will go this way instead of going 2. If you push 2 on the top, then you go the other way. So it does not affect anything over here. We just have to exhaust our search, find all the paths. This brings us to this very interesting point that every recursive function can be solved iteratively using a stack. You should practice this thing. It's in some problems, it is actually, it gives you a very interesting way to handle some cases, or it's something very good to know. I was asked exactly this question. I asked this question interview in Microsoft interview some 15 years ago. I solved it using recursively, and then they asked me, can you solve it iteratively? And I just remembered this thing. I never practiced it. I started doing it, and they realized, okay, I know that. Okay, stack can be used instead of the recursion. So, but it's a good tool to have. Learn. Okay. Let's do the next problem, which is all paths for a sum. Given a binary tree and a number s, find all paths from root to leaf such that the sum of all the node value of each path equals s. So it's the same kind of problem, right? So instead of returning true and false, we need to find all the paths. In this case, for example, the given sum is 12, and we need to find all the paths. So 1, 7, 4, 1, 7, and 4. This is this 1, 7, and 4 gives us 12, and similarly 1, 9, and 2. So traverse all the paths, and store all the paths actually, whose sum is eventually equal to the given sum. So the trick probably is we have to actually pass a variable which is instead. So in the previous problem we are dealing with the sum, so we are decreasing the sum and passing that sum to the next call. In this case, sum is there, but we need to pass what is the current level, the whole traversal of the nodes, and so that we can eventually, when we read at the leaf node, and if that leaf node is terminating at a path which gives us the required sum, we can actually store it in a result array. So let's see that. Okay. All right, little bigger code. So find path is the function, root is the tree's root, and this is the required sum. So we create a result array which contains all the paths, and we actually made a recursive function. And why is that? Because the two variables are there, but then you need all paths, and this is actually the current path. So just take the root and pass it 2 extra parameters. So all paths will store the successful paths, and this empty list is telling us what is the current path is. Let's see. So let me choose that again. So this is again, it's a very simple check, but this is your, like, you can say, the main final condition that will break your recursion. If we have reached a null node, which means there's no children right below it, we simply return it. Otherwise, just append the current node's value to the current path. Current path is that list. Okay, so and then what do we do? Current node's value is the required sum, and current node, the left is none, and current node none, which means if it's a leaf, So it's the same check from the previous problem, that okay, we have reached at the leaf, and leaf has the exact same sum that is required, and this leaf is actually a leaf. So at that point, we append the current path to the result list. And then if this is not the case, then we have to do two recursive calls. The same call to the left node and subtract the required sum with the current value sum, and pass the same current path and all paths, two variables, they're being passed. So similar code, similar check. Yeah, we were just appending, we keeping track of the current path, and whenever we are at the leaf, over here we simply return true in the previous, right? Or we have found a path which ends and we true. But over here we are creating, we are actually storing it in the result array. So, and let me see, actually. So there are two important lines over here. One is this, and the other is this. So let's first discuss this line. So this is for backtracking, if you know the idea. So what happens that we have this current path, right? So I have added that current node to the current path. So when I'm done with this thing, see, if I'm done with node 4, I need to remove it from my current path, so that when I go back, my current path is again 1 and 7, because okay, the current path was 1, then it become 1 and 7, and over here it become 1 and 4. So when I'm done traversing the children of 4, I need to remove myself from the current path, so that when I go back, the current path is again 1 and 7. So this is very crucial statement, because this is only needed because we are reusing the current path again and again. We are not making a copy of the current path to track all the nodes of the traversal.
Arslan,
Yeah.
so why not put this line on line 27, right after appending to all paths?
Line 27, this line?
Yeah, just before that. So basically the
Oh, yeah.
after line 26, basically in the same if block.
Oh, yeah. So yeah, so that is the other important statement I wanted to discuss. So what is your question?
So it sounds like line 37 should happen right after line 26. So why not put it right
Oh.
after line 26?
So this line is actually storing the current path, because now we have met all the requirements. Like in this state, let's say in this the current path will be 1, 7, and 4. Okay, because 4 is there because we have already appended the 4. Let's say, so this list fulfill our condition. Condition is it's equal to the required sum. So at that point, this is that path which fulfills our requirement, which is sum 12, which is not in this case, but I'm just saying it. So let's store this list in the all paths, which is the result array, so that eventually we have all the paths of the required. So this is done when we are going back of the recursion. So which means I need to remove myself. So to remove the effects of this statement, we need this statement.
I see. So this actually is common for whether or not we found
So yeah,
required sum.
Exactly. Since we are, so if the path is not found, remove yourself from the path and go back. That's called the backtracking. If even if you have find the path, so because you have to remove yourself, because let's say this was a successful path. For example, let me remove this is so much. So let's say this was our correct path. Then we go back to 7 and then traverse this thing 1, 7, and 5. So that could be another path. So you have to remove yourself. So to remove the effect of this statement, we have to do this statement. This is also needed because this line is actually creating a new list from the current path, right? If you don't do that, because current path is constantly updating. So this small statement can cause havoc if you don't put, for example, don't clone the current path. This list is cloning the current path because we're taking the current state of the current path, which fulfills our condition. Because this if is true, we store it in the result array, in the all paths array. So we have to clone that array at that point, because we are reusing the current path for other for all the calls, for other recursive calls, and even going back. So this is probably the most trickier part, that we need to clone the array, and this is required because we are reusing this current path for all the iteration.
That's because it's done recursively and not, I guess, iteratively.
Yeah. Other thing is, you can always clone it and pass over here. When you're passing it, for example, current path, you can actually create a new array and pass to the recursive call, which means then we don't have to do this thing. And since we create a copy of the current path and pass it to the recursive function, then it can be destroyed after the recursive call, or it will be destroyed automatically because no one cares about it. But since we are not doing it, in that case, space would space be more used? Make a copy and pass it to the, probably not, because the recursion tree will destroy itself, and we're making a copy at each level, either it is required or not. Yeah, in the worst case, it can have like the height of the system, height of the tree, and for each level we have a copy of the path. So in the worst case, since a tree could be a linked list, so we imagine we have a like this tree 1, 2, 3, 4, 5. It's like a linked list, but it's a tree. So you make a copy and pass it to this function. You make a copy and pass it to this function. So at this point, the memory used is actually order of n square. So that is why it's better to use the same array. So if you use the same array, then you are not making copy at every level. Which brought us to the interesting thought that what is the okay, there's a good discussion over here. Let me delete this thing. So space complexity is order of n. Also, the time complexity is order of n. We can calculate the Titan time complexity order of n log n. Oh, sorry. The time complexity is actually n square. Why is that? Although I just read it actually, it's because of this line. Although we are only traversing each node once, but this line is cloning your current path, you know. Cloning means traverse the whole list and create another list. So this is an order of n statement in the worst case, if the tree is a linked list, you can say. So that is why the algorithm's time complexity is n square, order of n square, worst case. We can calculate a tighter time complexity, like asymptotically speaking, could be order of n log n. It's a little complex idea, but the thing is, on the average, you can say how many nodes, how many generally nodes are there at each level. So the last node, if it's a complete binary tree, then the last node will have n by 2 plus 1 nodes. Like if you combine all nodes of the top levels, in this case, like 3 nodes overall, the next level will have, if all the previous levels have n nodes, the next level will have n plus 1 node. So similarly over here, if you see the 7 nodes, so the next level will have 8 nodes if in a complete binary tree. So which is a complete balanced binary tree, you can say, will have. So that is how we actually say that overall the height is actually log n. On the average, the height of this tree is log n, which is like, let's say 7 nodes. So log n is like, it's saying because overall on the average we have log n height of a tree. So that's why you can assume that the space complexity could be log n, and log n in this case. But in the worst case, definitely when a tree is a linked list, it's again it's an n square time complexity. So this line was very tricky. I've been asked many times. It's cloning, and this cloning takes order of n. That is why the time complexity is n square. All right. Let's quickly do this question. Given a binary tree where each node can only have a digit 0 to 9 value, each root to leaf path will represent a number. Find the total sum of all the numbers. Again, it's a very simple problem. The same idea that each leaf is actually a number, which is all the digits of the path. Like this 7 is a leaf, so 17 is a number, 192 is a number, and 199 is a number. So these three numbers, sum them up and return it. If you see the code, this is yeah, it's an interesting thing actually. So we call we created a recursive method. We got the root node only, and we need to find like all the sums that we can find. So for example, 3 number in this case. So we call it with we call it current node, and then the path sum, which is the current sum of all the whole traversal. This is again our the termination condition, and this is how we create the sum. We multiply the path sum with 10 and add the current value. It's like that, finding out the next, adding the decimal numbers together. For example, in the root we have 1. So what we do, the path sum is 1 here when I reach at 7. So how do we come up with 17? 1 multiplied by 10, and this becomes 10, and then we add 7 to it. So this will become like 117. In the next iteration, oh, there's no 7. Let's say in this case we have 19. So 19, and when we go to the 2, we multiply it by 10, 190, and plus 2 will always actually give us that number. So that is what we are doing over here. So this is the path sum, and then if so, if you remember the condition, if we have reached the leaf, and all the previous problem had the other condition too, in addition to the leaf, which is oh, we have reached at the required sum. In this case, we don't need to have that check, because we are summing up. We would just need to return the path, the current sum of all leaf nodes, so that when we are recursively calling, we are we are simply returning the sum, this sum thing, sum of the left path and the right path. So overall, we are calculating the path sum by adding the current node's value, and you can say calling the two children with the incremented sum and summing up both the numbers too, and this is our terminating condition. Any question or anything that is concerning or not you able to understand?
Just wondering, so in this case, we are not backtracking because we want to keep track of the previous sum, right? For example, in 192, once 192 is calculated, when we want to calculate 199, we still want to keep 19. So is that why we are not backtracking?
Oh yeah, so that's a good question. We are backtracking, right? I mean, we are going back, but why do we not need backtracking? Can anyone answer this thing? Why we don't need to like do that thing which we did in the last problem? Because going back, where we're not removing ourselves from the path sum. That's a good question.
Well, each sum is at the call stack, right? At the previous call stack has its own sum.
Yeah. What you meant, I guess, is it's passed by value. It's not passed by reference. So it's an integer variable. Everyone has their own copy. So remember all the discussion of making a copy of current path in the previous problem and passing that copy, and then you don't need to worry about backtracking or removing yourself. But over here, it's an integer variable, and they all be passed by value, you know. So we are making a copy of that integer variable anyway. So that's why we don't need to care about. So that backtracking or removing yourself is only relevant when we are using an object, because that object is passed by reference and we are changing the same object. Over here, these two variables, the path sum and path sum, we are making a new copy of that variable and passing it. This is how the, you know, the default behavior of primitive types.
Got it. That makes sense. Thank you.
Yeah.
Another question is, in some cases, or in the previous example, we have the base case, then we have the termination case, and then we do the calculation, right? But in this, you have the calculation right before the terminating case. Does that order matter? Can it be in any format?
Yeah, definitely. It's again a good question. So this condition, if I remember correctly, we have to, like in the previous code example as well, we have to add ourselves to the list and then see if we meet the condition, and then we can return or add ourselves to the all paths list. So so this is needed, right? Because if we say we are leaf node, so we at that point we return the path. Let's see. Let's compare it with the other ones. So in the ALPath problem, we add ourselves and then we have the if condition. Again, we are actually doing the same thing. We have to update the current state and then see if we have reached the terminating state and either return, or in this case, we have to append ourselves to the result array. What was the binary tree path sum? Yeah, so over here, it was only returning true. So there was no you know, state that we need to determine. So that's why, you know, so that line which you saw in other codes over here, it is somewhere here. That was not required. That's the nature of the problem. So overall, generally, you can say, so that state change needs to happen before we find out the overall restriction or the condition of the problem, and then we return or add ourselves. So that happens over here. But in this case, I mean, because we don't need it, that's why.
Got it. So it has to happen before that. Makes sense.
Yeah, it has to happen.
Thank you.
Yeah. All right. So I guess you guys have the idea. So let's move on to the I call it island pattern, or some people call it flood fill pattern too. It's a very famous pattern, but this will extend our you know, this breadth first depth first approach to the next level. So let's see, actually, let me quickly select all and delete. So matrix could be, you know, considered as a, when we want to traverse all paths of a matrix, we can consider it as a graph. So let's see, 1, 2, and 3, 4, 5, and 6, 7, 8, and 9. So this is a matrix. And let's say we want to traverse all paths. All paths means if we go here, here, if you want to reach here, or this way, this way, this way, this way. Imagine you can only go right, or right node, or the bottom node. For example, here, 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 and similarly we can go all the way here, here. So there are multiple paths to reach like the end from the top left to the top bottom, to the bottom right. So this can be considered as a tree traversal or a graph traversal. Let's say one has actually 2 children. You can go right or you can go bottom. So 2 and 4. Similarly, if you see 4 has 5 and 7. this. Oh, sorry, I did the wrong. So 2 has actually 3 and 5. So 2 has 3 and 5. 4 can be, we can go to 5 and 7. 5 and 7. Similarly, you can get, for example, from 5, you can go to 6 and 8. Right? So it actually is a tree. The only difference is, if you see, is for example this 5 and this 5, right? So we can reach this 5 from 2 and 4, because the 2 ways you can go, either in the right node or on the bottom node. So it is like a traversal, but it's not like a tree where we have a unique path to reach any node, you know. If you imagine this 5, if you imagine this is a tree, so there's always a unique path to reach this node or any other node. But if you consider a metric as a graph or a tree, then it has, like, it's not tree, it is a graph then, because you can say you can connect this thing to over here. So because graph becomes the graph, you can have multiple nodes coming over here and multiple links coming to a node. So the overall idea is we can consider it as a tree, and then we do breadth first or depth first based on the restriction of the problems. Let's see this thing in action. So this island pattern is very famous, where you are given a matrix with ones and zeros, and they say 1 is land and 0 is water. Find island. An island is a connected set of ones. 1 is land and surrounded by either an edge or a 0, which means a water. So for example, all these ones in this orange, they're connected, you know. So there's one island in this matrix. And how they are connected, again, from every node you can go either to the below node or to the right node. Some problems will tell you that you can go to the diagonal node to this one. So generally left or bottom. Yeah, otherwise, yeah. Go ahead. Someone saying? All right. So in this problem, we know that we are only going to the right node or the bottom node. For example, if you say this problem, so we have 3 islands. So none of these orange ones we can go to the, although it look like they're connected, but connection over here is restricted, that will either go right or bottom. You cannot go diagonal. So that is why you cannot go from this node to this node. I mean, you cannot go from this node to this node, because we are not allowed to go diagonally. So that's why we have actually 3 nodes, 3 islands in this matrix. So let's actually see the solutions for this thing. If you see what we can do, we can do, as soon as we find a 1, we can start traversing the matrix. As soon as we find a 1, we can assume that, oh, this is start of the island, and we can count it as an island and then traverse all the connected ones, either to BFS or DFS, and mark all those nodes as one island. So somehow we can mark, like we can actually make these ones 0. So start from this one node, start from this and do a BFS, like go right and go bottom, when you go bottom, there's already you don't need to go bottom because it's not one, so it's not part of island. We go right, so we make this one as 0. Then we go right, we make this guy 0 2, and similarly this 0 2. Marking means we can mark this node as 0, or we can use a separate array to see, oh, we have already traversed so this node. So that is how we exhaust our search in a breadth first way. So the restriction of the breadth first is we can go right or bottom, and if we encounter a 0, we don't need to visit those, so we can kill our BFS search over there. So when you're back, all these ones, all the oranges one becomes 0, and we have counted one island. Then we keep moving, so all these be 0, and then you can go here, you find another one and do a BFS and count another island. So this becomes 0 2. Then we do your search here, or you find another one, so count that, oh, we have 3 islands, third island, and then do a BFS to mark all these 1 0 2, and then keep iterating the remaining ones. You'll see, oh, everything is 0, then we can return. If we see the code, okay, so over here we can use both DFS or BFS. So let's see both approaches actually to see what's the difference. So again, it's a very famous category of problems. So you will always see this kind of code in many problems. And as we go through this problems code, just remember kind of this behavior, and you'll be, using this code in many other problems. So we only given a matrix, and we need to count all the islands in it, right? So remember, the strategy is iterate the matrix. As soon as you find a 1, count an island, and then visit all the connected adjacent using any DFS or BFS. In this case, we are doing DFS, and mark everything that, oh, this is part of one island, so that we don't count all ones as different island. Okay, so that's what we're doing it. This is the length of the matrix, and this is like rows and columns. That's how we find out how many rows or column the matrix has. This is just initializing a variable to count the matrix. Then we iterate all the rows and column, like iterate the whole matrix. If the current value of that matrix is 1, we found an island. So increment our count and do a DFS search to mark everything, so that so all the connected ones become one island. And once we're done with this DFS, this total island will contain the sum of the islands. So this is the main code, which is actually marking all the connected ones, or mark all the ones of one island as one island, so that they're not counted again. So what we are doing, we're calling it again the matrix and the current index, the column and row index. So this is our X, this is our Y, IJ, and the matrix is the main matrix. You'll always find this condition. What it is doing, it's saying if we are not going outside the boundary of the matrix, like X is less than 0, how can this be possible? Actually, over here, you'll see the recursive calls because of that. So we'll see. So X should never be 0, and X should not be beyond the number of rows. And similarly, Y should not be less than 0, and Y should not be more than or equal to the length of the or number of columns. So this means X and Y are the valid index of the matrix. So this beautiful check is ensuring that the X and Y are the two indices which is pointing to a valid cell of that matrix. So this is a very, very important, crucial condition. So this will always happen. If it's not, simply return. It's like that node or node we have reached at a null node or outside the boundary of the tree, so we simply return. So this check beautifully limits you within the matrix, and so that you don't like crash because of going outside the matrix and trying to find a cell which is not there. Okay, now since we are marking an island, so the cell which we are right now, if it is 0, imagine when we are here, imagine when we are here, if we go here, we don't need to call it, we can simply return. So any value which is not 0, it's not an island, and we don't need to traverse, we can simply return. And then what it means when we reach here, that this is a valid cell and this cell is 1, because if it is 0, we already return, it is not valid, we have already returned. So now let's mark it part of this island, which is change the value of this matrix to 0. So now we have marked it. So now call all the adjacent cells and call recursively, so that we can mark the other adjacent cells too. So we are doing actually 4 calls here, which is a little strange, because we said we can only go to the right or to the bottom, right? So this is the lower cell, which is fine, and this is the right cell, which is fine too. So this is actually your like upper cell, and this is the left cell. So I think I said wrong. Each cell is considered connected to other cells horizontally or vertically, not diagonally. Like you can go actually in the 4 directions. It's not that we cannot go actually upper cell or the left cell. Probably I confused it with another problem. So this is an important reminder that on each cell, if it's not, it says connected. So you're connected to actually horizontally and vertically, means top and bottom and left and right. So x plus 1 means the next row and the same column. X minus 1 means the previous row and the same column, then the same row and the next column, and the same row and the previous column. So we have to make 4. So when we are so this is needed. For example, we came here, this is fine, but now we have to go back, so this left call is this left call actually is actually ensuring that we go back too. So we mark here, or like here, and then here. So that is how we end up marking all the nodes. In all the matrix problem, actually you will do this thing, that you actually go in all the 4 directions, or like I don't remember if there's any problem, but you can go actually in the 6 directions too, if you're allowed to go diagonally, this one and this one. Okay.
If this did allow diagonal, can you show maybe how you would change?
Oh, yeah. Let's do that. Let me do this and do this, right? So this will be self dot, I can actually. So visit, this is BFS or DFS? Okay, DFS, right? So what will we do? Matrix. So diagonally up, diagonally down, let's say x plus 1 and y plus 1, right? So that would be, for example, if we are here, so this would be diagonally down. So this call is x plus 1, next row and next column, okay? And similarly, if we wanted to do the other one, as you might have guessed, it would be x minus 1 and y minus 1. So that would be diagonally this one. Got it?
That makes sense. Thank you.
Yeah, yeah. All right. So, so what is the time complexity? Let's say. So what could be the time complexity here? What do you guys think?
Row into column.
Row into column, right? So these two for loops are actually telling us that we are doing row into column, but then we're doing this visit land as well, you know, and it is it can end up traversing the whole matrix if I remove these two lines. Do you still think it's row into column? So essentially we are saying that, asymptotically speaking, this which is right actually, this line is not increasing the time complexity. So one thing we know that so this DFS will you know will mark at a max level, will mark each node 0. Let's say we're given a matrix which is all 1, right? All 1. So as soon as you find an island, you call it this, and this will come and it will actually end up traversing the whole matrix and mark each cell as 0, right? So this is again a row into column thing. So once we are doing row into column, and then this guy did row into column as well, right? Now, but what happens when to go to the next node? The next node is all 0 again, right? So this condition will never be true in the worst case, I'm saying, because we have marked the whole matrix 0 because the whole matrix was on an island. So asymptotically speaking, our time complexity is 2 into row into column. And since we removed the constants, that's why it's order of row into column. I guess that's what we have, but I don't know, yeah, we have discussed here. Yeah. Where m is the number of nodes and the number of columns in the input matrix. This is due to the fact that we have traversed. Yeah, this thing they have not mentioned. DFS and the space complexity is because of these recursive calls. The space complexity is also row into column. Can anyone explain this thing? Why the space complexity or the recursive calls cannot go more than the number of cells of the matrix? So anyway, like, so one, it's because of the recursion tree, right? We know because of the recursion tree, we can assume that, right? And in the worst case, as I mentioned, if the whole matrix is 1, you end up making how many calls? Row into column calls. So your call stack can be as deep as number of the cells of the matrix. So that is why you say that the space complexity is also order of m into n. Any question over here?
Yeah, one question. Is it good to, I guess, no, is it ideal to do this in place, or do we want to create like a separate visited matrix to keep track?
So that's an interesting question too. So personally, I don't like this strategy. Generally, you are expected to not change the input array. The input array should be the same. Even if you are changing the input array and then reverting it back, that is even not considered allowed in many, you can say, real problems. in an interview, you can I personally like if you use the matrix array. We will actually see the code when we use another array to mark nodes as traversed. Why? Because of the same reason. Generally, it's not. You can if you want to ask the interviewer, I don't know, if you wanted to ask, or you can even mention this thing. Oh, we can use in place, but since you don't intend to change, you don't like changing, or I mean, you don't need to. You can actually add a a new matrix which will retain the state or visit it or not. But would that increase the space complexity? It would not, right? One is because of this recursion. Of course, DFS definitely, since it needs order of m into n anyway. So if you use another matrix order of m into n, that would be the space complexity would be 2 into m into n, which is again m into n. So space complexity is not like affected over there. And the second thing is, even when you are changing your input array, this is considered as using that space. So again, I mean, you should say that, oh, since we are using the input array, so like either you're not increasing the overall space usage, but since you're using it, so at some level, you can say that, oh, we are actually making use of order of m into n space. So it's overall 2 into m into n, because we're using the input array and the matrix and the recursion. That's why it's order of m into n. Yeah. When we see the next BFS approach, I think then this discussion becomes more valid. So let's quickly see that. So again, the same code, same total island, and we say now visit BFS. And remember how we do BFS? We use a queue. And in this queue, we push an element. Which element? The element is the current index, the cell, you can say. Then we have this while loop. We keep doing it until the queue is empty. There's no recursion here. See, so DFS is all recursion, but BFS is only a queue. And until we have until the queue, the neighbors, we call it, the neighbors queue is not empty, we keep iterating. We get one element from the queue, and if it's not valid over there, it was recursion, so we return. Over here we continue because there's no returning until the queue is empty. So it's the same check, except that in the recursion we return. Over here we continue, and then over here, if it's 0, again continue, means if it's not 1, and if it is 1, we mark it 0, and then we add four cells to our queue, right? So this is a DQ. So we insert or extend, we call it, to all the lower cells of the same kind of code, but instead of making a recursive call, we have this queue, and in that queue we actually have all the cells that we need to traverse. And until that thing is open, the queue is not empty, we keep traversing. So over here, if you see, what is the space complexity? There's no recursion, but the queue, can
extend here too.
Say it again.
What extend does here?
Oh, extend is like inserting or extend your queue, add this element to the queue. I don't remember exactly. There is this extend, and you can insert an element. What does extend? What's the difference between extend and, I forgot. I'll send you guys a note later why there's extend. But it's essentially we're adding an element to the queue. So all the 4 directions we add it and go back in the while loop over here. I don't know.
I believe extend just adds it to the end, but since it's a double-ended queue, you can use insert.
Yeah.
0, so you can add to the other side if you want.
Yeah. All right.
Also, where are we adding the islands here?
Oh, well, there's the same way. As soon as you find a 1 increment your count and mark all the connected cells. Yeah, it's the same code, except very smartly. If you use this line and this line, and these were the recursive calls in DFS. Over here, we're just adding things that we need to visit in the queue. Let's see so overall, if you see because of this line, or when we are extending it, so the queue, what is like the time complexity is, again, you can assume the same, right? This I and j are the same, and then this traversal can happen once for one for each cell. Anyone has a question? The space complexity, we can, like, this is the core DFS. The space complexity is actually a little complex. It says min of m into n. Why is that? So this space complexity is based on how many elements we can push into the queue. So this is a little tricky, that how we do it. Let's see.
Because one is using the tuple versus the actual like values. So like line 21, we're basically storing the tuple as opposed to the other one.
Oh yeah, that is fine. I'm saying how many tuples you at max you'll be pushing. Oh. Because you're pushing 4 elements here. Let's see a matrix. Let's say, for example, this is a 5x5 matrix, right? So so when you are at this one, let's see. Oh, let me actually. Yeah, if you are at this one, you'll push, for example, one element and two element to it, right? Let me make it a little black. So let's say then you start traversing this element, and then you will push this and this. At this point, you have, let's say, this and this. You have 3 elements, right? So these 2 and this one. Let's say you now remove this element and add this and this. So 1, 2, 3, and 4. You have 4 elements. So if you get rid of this thing, push 2 elements. You're taking 1 element out and adding 2 elements, right? I mean, in the case. So 1, 2, 3, 4, and 5 elements, right? So then you take this element out and push this element in the queue. So again, you have 5 elements. So then you probably you take this element and push this one, and this you already pushed. Yeah, you have to push this element because we are not making any check. This element is already in the queue, by the way. But since I'm traversing this element, I push this element again. So 5, 6, and 7. You have 7 elements in the queue. If I'm not saying it wrong. So now you take this element, 1 element out, and push again 2 elements. If everything is 1, am I saying right? That we have to push both of them. Oh, yeah, we won't push actually, because of that if. No, I'm saying wrong. Yeah. Let me quickly see. Because of where are we? Is this BFS? This is BFS. So because of this thing, these 2 conditions, of course, we are not going out of boundary, but as soon as you mark a node 0, you actually don't push its neighbors over there. So what I'm saying, that when you are for example, here, let's say, so you don't push actually this one or this, you actually push this one. Yeah, if you go back to 0 again, because this thing is already 0 and this thing already 0. So anyway, I think, so what happens that you take one element and try to push like 4 elements into it because of the 4 neighbors. Like if you are on this node, you will actually end up pushing 4 elements. But let's say when you take out this element, you don't push. Like if you have already visited this thing, this will become a 0. So at that point you will not add since you continue over here. So that is why this time complexity becomes order of m into n, my minimum of both the values, this one. At a high level, you can say it's order of m into n, but the tighter asymptotic is the recursive call is we are making, or not the recursive calls over here. We're pushing the elements to the queue, but we take one element and try to push all the 4 neighbors. But if you try to understand the neighbors that you have already visited, you return from here. So at a certain level, you cannot have like all the matrix like m into n rows, m into m, n into m into n cells in that in your queue. So that's why it says like either it's all the columns or all the cells. Actually, it will be 2 or 4 into m actually, but because of the like actual time complexity would be, I think so, it's order of minimum of 4m or 4n. So that would be the time complexity. And since we don't take 4 in the time complexity, that's why it's a minimum of 4. Because 4 is because you are taking the 4 cells. So in the worst case, you have 4 nodes pushed into number of, if you have like 5 columns, you might have like 20 cells pushed into the queue at any level. I don't know if I'm able to explain it a little, but you guys can think about it, and if you still have some questions, we can discuss in the next lecture. Oh, we already 7:43. Yeah, go ahead.
Are there any companies that, like, I guess this pattern is like pretty common, or at least you've come across?
Oh, in the actual work
for the island one, because I've never seen it, so that's why it's new to me.
Oh yeah, I have. It's been asked to me in an interview. Yeah.
I had one question from Amazon. The question is, there are developers in the room. They are sitting in different location, and they want to put a coffee machine. And the coffee machine should be closest to each developer. Where should we put it? A kind of similar DFS. Not the island, but you have to find the closest one.
Yeah. So yeah.
The ones shows you the pet, and you put the coffee machine. Let's say 4 developers sits in a different metrics.
Yeah, I get it. So yeah, one of the problem is quite linked to this problem that you're suggesting. I don't remember which one is that, but yeah, it's the closest. The distance is between 2 nodes. You have to minimize that distance.
Yeah, they trick like they put like 4 developer different pets. You have to calculate all of them, add them up, then come up with minimum sum.
I was asked this question, and this was a geographic company, and they have this problem where they wanted to mark some regions. So they are the map of cloud and non-cloud areas. So you can say ones are cloud and 0 are no cloud, and they wanted to find the island of clouds. you can say, so they have the geo data and they have the squares of each, and to estimate probably the size of the cloud, the space, either for the aeroplanes, or I don't know what they wanted to do. So like he made this problem a little interesting, where there's no water, but it's a cloud or no cloud. And then we need to find out how many different areas of the cloud are there. I think that problem is probably the biggest island kind of problem over here too. Any other question? Otherwise, I wanted to quickly go through this visited metrics thing. Any other question? All right. So again, we discussed that thing before, right? So let's have a separate matrix. Instead of actually marking your node 1 to 0, you can have another matrix, and that matrix has the same number of rows and columns, and everything is false by default, like, which means you have not traversed that cell. Same code over here, but this line, now we say either the matrix is, the value is 1, that is why we are incrementing, but then we have also another check that we have not visited, because this check was not needed, because once we visit, we mark that node 0. So this condition will never be true. But in this case, since we are not changing the original matrix, so this 1 will always be there. But because of this visited thing, which means, if it's not visited, then I visit and increment and do the same BFS search. But how we do it? The same code. You have the, let me remove this thing. The same code, Q is there, pop left is there, and this is the same check, continue. This is the if it's 0 or visited, again continue. So this is an extra check we need to add. So this check and this check is the only difference so far. And then, okay, this is the difference, another one. So these 3 encircled lines are the change. So over here, we were doing the 1 to 0. So instead of 1 to 0, we mark that cell visited by making it true, right? And the remaining code is same. So yeah. So this check and this check is ensuring that either the cell could be 1, but we'll still visit it or not visit it, because based on the visited column. So this is that other code that we wanted to see. Okay. Any questions so far? Otherwise, I think yeah, you guys got the idea. It's a very interesting pattern, this one. I've seen problems of this pattern, like I've been asked this question. It was probably the flood fill. I think it was the flood fill algorithm. It's a famous flood fill, the MS Paint. So all the connected regions, you have to paint a different color, let's say. So it was 1 1 1 1 1. All the ones will be a new color, which is like 2, a different number, you can say. So flood fill is a famous algorithm that is being asked. It used to be very difficult question, but now over time, this has become an easy question. That is how these coding interviews are becoming more difficult and more challenging for humans.